Good afternoon to one and all present here. In this pleasant afternoon, on behalf of the Department of Physics and Chemistry, Sona College of Arts and Science, I welcome you all to this webinar on applications of liquid crystals by our chief guest, Professor Lakshmi Narayana M Mohan, sir. It's my great pleasure to welcome our chief guest, Professor Lakshmi Narayana M Mohan, sir, and I welcome all the professors and participants to this event. Now I invite Dr. Sridharan, sir, Head Department of Physics and Chemistry, to give presidential address.
Thank you, Adisha. Very good afternoon to one and all present here. It's a pleasure being here to welcome you all. And in particular, today we have a senior professor. We all learn from him. So today we have a speaker who has a vast research experience as well as teaching experience behind him. So I'm really thankful to Dr. Madhu Mohan sir for accepting our invitation. He's very busy teaching, doing research. In spite of his very busy schedule, he has agreed to be here to talk to us on applications of liquid crystals. So I sincerely thank you, sir, for accepting our invitation and being here with us on time, as you said. And I welcome all the participants. Today, I hope all of you will take home some points worth remembering today. So I hope all of you will have a very good session ahead. And without taking much of the time, I welcome you all once again on behalf of the Department of Physics and Chemistry, Sona College of Arts and Science. And I welcome you, sir, in particular, and thank you for accepting, and thank you everyone for joining us today. Thank you.
Thank you, sir. Now I invite Dr. Shankara Narayanan, sir, to introduce our honorable chief guest to the audience.
Good afternoon to everybody gathered here. Today, I deem it as an honor in introducing chief guest of the day. Words could not suffice to tell about you. Our chief guest is a man of virtue and simplicity. I feel elated to introduce him to everyone today. If one takes a closest look at the alchemy of achieving person, two distinct virtues pop up besides perseverance and hard work. Those are his pro-thinking and thought-providing spirit. Our guest of honor and the speaker today is the living example of every being. Now we're going to introduce him. He has done his BSc Physics in AC College, Guntur, and completed his MSc in Microprocessor in Nagarjuna University, Guntur. He received his doctorate in liquid crystals at Nagarjuna University in the year of 1995. His research career started in Nagarjuna University as a research associate, and his teaching career starts as an assistant professor in Dr. Samuel George Institute of Technology. At present, he is in the Banariaman Institute of Technology, and he owns a liquid crystal research laboratory in that institute. And he has published 126 papers in reputed journal with good impact factors. And he has guided 6 PhD scholars, and 1 scholar is currently doing his PhD under his guidance. And I am proud to state that I am the student of his students. And he has received many of the funded projects from the funding agencies like DRDO, DST, AACT, BRNS Mumbai, SERB for about 90 lakhs. And it is our great privilege to have Dr. Lakshmi Narayana M Mohan as our guest speaker. As an experienced personality and speaker, he brings wisdom and knowledge to the audience. Thank you, sir.
Thank you. Thank you for all the good words by Dr. Sridharan, head of the Department of Sona Arts and Science College, and also Shankar Narayanan, whom I know as a scholar in my laboratory, guided by my student. And I thank the management of the college and the principal for giving me this opportunity. So before starting, just let me tell you that I'll be talking about liquid crystals, which are used everywhere. And I'll not be talking about the synthesis or the characterization. I'll be talking only the application perspective of that. So I'll start my lecture. Before that, I just want to have an invocation. So this is Bhajagovindam. He says that in this that how we need to reach the God. So this is all the prayer which we need to start. So the saint from the Kerala talks about how the non-attachment should be there, and from non-attachment we go to the freedom of delusion, and from there we go to the liberation. This is what he says there. Now I start my lecture, and here we have I want to introduce to 4 levels of my lecture. The first level talks about the hydrogen bond, which is available everywhere. Then the second, in the first level, in the 0th level, I talk about the hydrogen bond. In the first level, I talk about the hydrogen bond, which we are talking in specific to the liquid crystal. To be more specific, thermotropic liquid crystal. That is, temperature, the phases will change. That is what we call thermotropic liquid crystal. Then in the second level, I talk about what are the types of we call it hydrogen bonded liquid crystals. And then in the third level, some new orderings which we found in our laboratory, and finally I'll take you to the applications. So this is what we call the agenda of the talk. Anywhere, if you have any doubt, you can just interrupt me. I don't get annoyed. It's a pleasure to answer your call. So what is hydrogen bond? In fact, hydrogen bond, we talk about covalent bond, we talk about van der Waals forces, we talk about ionic bond. These are all different types of bonds which are available. Now you talk about a hydrogen bond. What is hydrogen bond? This is one type of bond, and the length of the bond depends on many factors like pressure, temperature. If you take water, you have H2O where you have the hydrogen bond. Hydrogen is bonded with oxygen, and the way it bonds gives you some different, for example, you can see the water as a solid, as a liquid, and a gas. And in 3 states, the hydrogen bond will have different formations. Now, the bond strength, this is what I said, it depends on temperature, pressure, angle, environment. This is what, if you take the water, boil it or freeze it, the bond varies according to the temperature. That is what we mean there. Then in water, it is, you can see the number has given 197 pm. This is the type of the length of the hydrogen bond, we call that. And the bond angle depends on the donor hydrogen. If you take hydrogen, it is a proton donor, that is what we call. So there should be an electron acceptor. So these two constitutes how the bond will be. And there are different types of acceptors and donors which will be seen. So in this slide, what we understood, we said what is a hydrogen bond, because there are different types of bonds available. That is covalent, ionic, van der Waals forces. In addition to it, we have a hydrogen bond. Then we also said that bond will vary with temperature, with pressure, and with environment. And also we said that in water, which is very persistent everywhere, the length we talked about. Now this is how you can see the same hydrogen bond. I'm talking about the hydrogen bond. Hydrogen is bonded with different acceptors and donors. You can see here. So this is HF, fluoride, hydrogen fluoride. And you can see other things over here. So the symmetry varies. The hydrogen bond is same. The symmetry here, it is linear. Here it is trigonal planar. Here it is pyramidal, so on and so forth. And the angle also varies. You see the highest angle to the lowest angle. 46 is the lowest angle, highest is. So this hydrogen bond, though it appears to be similar, the symmetry and the angle varies with the donor. So this is what we understand here. How is the strength of the bond? So we have seen here, what do you mean by strength? Probably you may be knowing, to break the bond. If you want to break, for example, you take sodium chloride and put it in water. A fellow who has not read the science will say it dissolved. But a student of science will say that the bond is dissociated. You have Na and Cl, which is we call the ionic bonding. The bond is, how the bond is dissociated. Water has the capability to break the bond. Similarly here, to break the hydrogen bond, we require this much of energy. So it all depends on to which it is associated. So you can see here the kilojoules per mole or kilocalories per mole. This is the unit. You can see depending on the bonding, you can have, it can be a very weak bond where 1 to 2 kilojoules are required to break it, or it can be extremely strong in hydrogen fluoride, where you require maybe 160 times of this, 161.5. So the strength of the bond depends again on, because we don't say this is ionic bond, we don't say this is covalent bond, but in hydrogen bond, it all depends on the environment, it all depends on the bond angle, it also depends on other factors like the donor and the acceptor. So this is what we say here. Now, what we see, where we see hydrogen bond, people will appreciate if I say that water is most glorious example of water, because in water which is, whether it is a sea water, marine water, whether it is a fresh water, if it is water, you have hydrogen bond. So this is what we call. In a discrete water molecule, there are 2 hydrogen bonds. That is what we know, H2O we call it. And 2 molecules of water can form a hydrogen bond. So the way the hydrogen bond can be seen is in water. Whether water is marine water, whether it is salt water, whether it is distilled water, whether it is triple distilled water, whatever it is. If it is water, you have hydrogen bond. That is what we say here. So how it is that you have, H2O, 2 hydrogen bond, atoms are bonded to the oxygen, and that is what is being told here, where it is formed. Now you can see here, we can see this can repeat in water molecules. The so-called, this is what I had drawn here. You can see the hydrogen, which is red in color, and oxygen white in color. This will be replicated, and thus you will be getting many what we call hydrogen bonds in water. Now, hydrogen bonding strongly affects the crystal structure. No, I just told you, water, you freeze it, it becomes ice. Ice is much stronger than water. So usually people, when if you see some detective movies, all that, they use ice as a weapon. They make it as a knife, so that the other person will not be knowing later on. When it melts away, you will not be knowing with what weapon the murder was done or attempt to murder was done. So here, what I mean to say is, when you take water and you freeze it, it becomes, the bond becomes extremely strong, and that is what it says. You can see, helping to create an open hexagonal lattice, because we talk about why the hydrogen bond is very strong in ice, because of the hexagonal lattice. And the density of ice is less than density of water. Probably when we are teaching students, we'll be telling them what happens if you take ice and put in water. Obviously, ice will, it floats on the water. But if you take any alcohol and put the water and put the ice cubes, it dips. Here we are not talking about the alcohol or the water. We are talking about the density. If the density, you are taking a liquid and a solid. If the solid density is less than the liquid and solid density greater than liquid, the floating and sinking will happen. So this is what we show here. We are just talking about the trying to understand the hydrogen bond in water. You can see here, well, if you are not interested in water, where else you can find hydrogen bond? You can see here the DNA. Everyone will have our own DNA. And you can see the DNA. This is what we call, by the way, there are left-handed people and right-handed people. The DNA, as you can see here, is a helix. It forms a helix. You can see the helix. And this, if it is levo and dextro, levo is left-handed, dextro is right-handed. So if the left-handed people will have a helix wound in the opposite way compared to that of the right-handed people. Coming back to hydrogen bonding, you can find hydrogen bonding in DNA. So these proteins and these nuclear bases, all when they form bonds with hydrogen, then there you will be getting, you can see the macromolecules forming there. And also the double helical structure, I had shown here 2 helix. This is a double helical structure of DNA. This is because of hydrogen bonding. If there is no hydrogen bonding, you don't have any DNA and you don't have any species to live on the planet Earth. So water, which is very essential, contains hydrogen bonding. DNA, which is again very essential, contains the hydrogen bonding. And this is what we say. So this is a complementary strand. What is complementary? I'll be telling you later on. We have a pi stacking So when you talk about benzene, we talk about pi. We talk about what is pi. There, the pi bonding is what we call is essential. It is called conjugation. It is essential because it carries the electrons. Thus, the electric flow will be there. Anyway, here in DNA, you have a double helical structure, and this is because of the hydrogen bonding. And this is essential. We can see here. This is the backbone of it. That is what I mean to say, as far as the hydrogen bonding is concerned. Now we'll come to our liquid crystals. So, what is hydrogen bonding in liquid crystals? So, in hydrogen bond liquid crystals, there are complementary bonds are there. What is complementary? Probably when you go to any function, we'll give some gifts. When somebody is getting married, we go and give gifts. And reciprocation will be there. When we get married or when some of our people get married, they'll come and return. Not return the same gift, buy something and return it back. This is what we call, this is not complementary. This is called, you give something and it will be, in return, you'll be getting something back. And here, what is then complementary? Complementary. The English meaning says compliment. What is compliment? If you do anything good, the teacher will appreciate you. So anything appreciation is called compliments in English dictionary. Then what is complementary? You have an electron donor and an electron acceptor. When a bond is formed between a donor H and an electron acceptor, maybe oxygen, this bond is also called as complementary bond. So here what is complementary bond? A proton, which is and an electron. Proton as an acceptor, electron as a donor. They form the bond, and this is what we call. And usually these hydrogen bonds are very weak bonds. What do you mean by weak? We can go back to the slide 2, where I have shown you the energy required to break the bonds. So when you have little energy, it is easy to disturb that bond. So that's the reason it is called a very weak bond. So this is the hydrogen bonding in liquid crystals. Well, a little introduction to liquid crystals. What is a liquid crystal? Probably if you are wearing a watch, and if it is a digital watch, certainly you are possessing a liquid crystal with you. Any display as of now in the world, any display in the watches is of LCD type, that is liquid crystal displays. What is that liquid crystal? It exhibits the properties of liquids. What are the properties of liquids? You take different, what we call the density, or you take, these are all the ability to flow. We call that viscosity. So if you take viscosity or if you take density, these are the properties attributed to liquid. And what are the properties of solid? Solid has a three-dimensional structure, that is, we call lattice. So a liquid crystal in total will have the properties of liquid and the properties of solid. Both will be there in a liquid crystal. This is what we call liquid crystal. There are classification of liquid crystals. Viscotics are there, thermotropic liquid crystals are there, and so on and so forth. We are talking about thermotropic. What is thermotropic? If you give temperature, the liquid crystal will vary from solid to liquid. So this is what we call thermotropic. So in thermotropic liquid crystals, this is the title, we are talking about the hydrogen bond. So hydrogen bond can be formed by complementary, that is a proton acceptor and electron donor, and this is what we call the H bond in liquid crystal. Now I just want to show you a movie. This is a formation of liquid crystal. What is that I did? I took a slide and rubbed it in unidirectional many a times. So these grooves are formed. So I kept my liquid crystal and heated. You take any liquid crystal, you see when it is flowing in a groove, at the end of it, it becomes a crystal. So you can show how the liquid crystal, we have what I should call it, picturized it in this laboratory. So what is a liquid crystal? It is a liquid and a solid. So both things can be seen. So here what we did, we took a glass slide and we rubbed in one direction many times. Why we rub? To make micro grooves, and then we kept the liquid in that and heated. Then you can see what happens. See what happens? It starts to, you can see here, this is all the grooves in which the liquid is flowing, and you follow one, it becomes crystal. So this is how the liquid crystal formation of a liquid crystal. Just to tell you what is a liquid crystal, how it is formed, we have shown you this so that you can appreciate. So this is one texture we call it, and if you cool it, you can get the crystal. Since it is just formed from this isotropic liquid, what is the difference between a crystal and liquid? You see, the liquid crystal will be very bright, crystal will be very dull. That's how we distinguish the liquid crystal and the crystal. So this is the formation of it. Now let us go to hydrogen bonding. So you can see how the hydrogen bond is formed. So here, this is a donor, hydrogen donor, and this is an acceptor. So you have a bond between N and H. Here you can see O and H, acceptor and a donor. So you have a bond between O and H. So similarly, I can show many things where you can form the hydrogen bond. The hydrogen bond can be formed between what we call oxygen. You see, we call electronegative and electropositive. If you can classify the atoms between electronegative and electropositive, you will be getting all these things. So this is what we mean to say with using this simple technique, that is the acceptor and the donor, they can form the hydrogen bonds in liquid crystal. Now, if you go, what is a polymer? I'm just going a little away from the topic. Polymer is nothing but if you take one type of chain, and if you multiply poly, what is that poly many? So if you can multiply that units many number of times, and that is what we call a polymer. So here we can use the polymers. You can create the polymers by what we call hydrogen bonds. So you can see many polymers are strengthened by hydrogen bonds. And we have synthetic polymers, and they are nylon. You know why the name nylon came? This nylon, this is collaborative work between New York and London. And so they have taken the names New York NY and London from London LON. So this is how the name nylon is formed. Anyway, this is the best synthetic polymer where you have repeated units. That is what I am saying. And this is, so in polymers also, you can make what we call hydrogen bonds. So this is what we call. And the bonds occur between carbonyl, ammonine groups. You can see the different types. Usually what we do, we take a acid group, COOH, so that you have there H and O. And if you take this, you can segregate and make bonds again. So this is what we are talking about, carbonyl or amine or amide. There are different types of group with which we can form the hydrogen bonds. And you can see the effect is great in aramid fiber where the hydrogen bonds stabilize the linear chain. So here what is that we are talking? We are talking how the polymers sustain, how the polymer strength will come. The polymer strength will come from the hydrogen bond, and this is what we mean to say. Now you can see a structure, para-aramid structure of where the hydrogen bonds contribute to forming the polymer structure. Then we go to now with what we can make hydrogen bonds. We can make hydrogen bonds with many things. For example, alcohol. OH is a functional group. So you can take atom where it can react with O and H and form the hydrogen bond. So you can take an atom which is having hydrogen, and so that it can form the hydrogen bonding in alcohols. Then you can have phenol, you can have amines, you can have amides, you can have carboxylic acid, that is COOH. This is the acid functional group. Even using COOH, you can make groups. These are all the functional groups with which you can make hydrogen bonding effectively. Now, in our lab, we are using dicarboxylic acids. So I said acid. What is acid? COOH. What is dicarboxylic acid? Two acid groups are there. You can see the compound, the chemical formula, the structural formula. All these excellently form hydrogen bonds. And to be more precise, all of these are liquid crystals also by nature. So you see oxalic acid, You then CH2 go on increasing CH2 group. Then you can get different acids, succinic acid, glutamic acid, malonic acid, adipic acid. All these acids will be coming, and all these are called dicarboxylic acid. Using dicarboxylic acid, we can make, this is already a liquid crystal. You can bring some other material and you can form a hydrogen bond with this H which is available, and you can make what we call a hydrogen bonded liquid crystal. And I want to show you one more movie. This is called switching. When this is a symmetric C phase, you see, when field is given, it switches. What do you mean by switching? It becomes bright. You see my cursor. This is bright and dark, bright and dark. So this switching, if is there with the field, then that material can be used for displays. You can use for displays. You can use for many industrial applications. So this is what we call switching. A liquid crystal scientist, when he makes a liquid crystal substance, first checks if it is ferroelectric. The star indicates ferroelectric. What is ferroelectric? You take the carbon, which has 4 valencies. If at least one valency is different with the other 3, then it is called ferroelectric, or it is called optically active, where the plane of polarization, if you send electromagnetic wave, and if it passes through that material, the material will change, alter the plane of polarization. This is called optically active. These optically active, or what we call ferroelectric materials, are readily available in the market. You need not synthesize. They are readily available. And these materials alone will be used in displays. You can see here, this is also recorded in my laboratory. You can see the switching, excellent switching. We have given some small field of 5 volts per 10 microns. And this is visible. You can see maybe 5H. So the dark and bright. So this is what we call the switching of liquid crystal mesogen, which can be used only if it is switching. It will be used in displays usually. Then what is that we did? I come to the types of HPLCs. I told you we can make what we call liquid crystals. So you can see here, if you can identify, this is the benzoic acid. You can vary the N, and then you can get different benzoic acid. This is another benzoic acid, and this is what we call a hydrogen bond is formed with benzoic acid with succinic acid. This is the succinic acid moiety. So this succinic acid, since it is a dicarboxylic acid, it is having 2 acid groups. We add 2 moles of benzoic acid, and there is a synthetic procedure. If you do that synthetic procedure, you will be getting this liquid crystal moiety. And you can see here we have done the characterization. So we varied the carbon number. This is the carbon number. And then we have seen what are the phases that is exhibiting with respect to the temperature. And this is what we call the phase diagram. So here it is exhibiting pneumatic, C and G. These are the phases it is exhibiting. And this is what we call the FTR spectrum. From the FTR spectrum, we will be knowing each functional group will give rise to one peak. So here the OH and CO, C double bond OH will be giving, there will be corresponding peaks, and this is what all about it. So this is published in 2010. This is some work which we have done. And you can see there are some other things which are interesting. We call about field induced transition. First, let me tell you what is a transition. What is a transition? When a boy is growing, adolescent stage, childhood, adolescent, middle age, old age. These are what we call 4 stages in a person. There will be a transition from childhood to adolescent. When is the transition? When you complete +2 and when you come to a degree, when you are pursuing your degree, that is a transition from adolescent to from childhood to adolescent. Once you complete your post-graduation and joins a job, that's a transition from adolescent to adult. So these are different transitions. So if you take water, if you freeze it, it becomes ice. At what temperature it becomes ice? It is 0 degrees centigrade. So 0 degrees is the transition temperature at which water will turn to ice. And if you take the water and again boil it, at 100 degrees it becomes steam. So 100 degrees is the temperature at which the phase transition occurs. So similarly, here we found transitions which usually transition come with temperature. But when you give field, what is field? V by D, that is voltage by distance. Then the transition is induced. These are called field-induced transition. So we have studied these field-induced transitions, and these transitions are classified as E0, E1, and optical shutter. This is one application I'll be showing you when it comes to the plate. You can see here, this is a liquid crystal conducting cell, that is glass plate on which ITO coating is given so that the transparency is not there, but the electrical contact is there. So I filled my liquid crystal into that. This is the conducting part. This is the non-conducting part. Then what I did to the conducting part, I gave some voltage. When the voltage is above some value like 5 volts, what happens? Optical shuttering is there. That is, the light is not allowed to pass. Excuse me. Sir, I'm in a meeting. I'll call you later. So this is what we call the optical shutter. When I give 5 volts, we'll be having what we call the light is not allowed to pass. And in between 0 to 5 volts, you have what we call frequency hopping. That is, the blue light is becoming red, as you can see here, red or orange, whatever it is. So this is called optical shutter, and this is called frequency hopping. So this is one application. So where these optical shutters are used, when you see your cameras, what is a camera? You have to allow the light to pass through it, and you have to shut the light. Usually in olden days, we have what we call the mechanical devices to shutter the light. Now with liquid crystal, if you give a pulse of 5 volts, then light will be shuttered. And if you remove the pulse, then light will be allowed. So these shutters, or you can use it as what we call, these shutters can be used in extensively in many places. So one typical place where I told you is a camera, where instantly in mechanical devices, it may take time to what we call get off and on. But here, if you give 5 volts and in milliseconds, the light will be shut. So this is an optical shutter. So it all depends on the voltage, and in between you can also have frequency hop. This is what we call the application, first application. Then going, why it is happening? Why the shuttering is happening? I've shown you, this is the liquid crystal, these are the mesogens. How at the atomic level, this is how you see them. This is the director. And now with the director, they are making some angle. Now when I give field, what's happening? These are moving, these mesogens. Now they are coming this way, this alignment, when the light is not allowed to pass through. And this is what we call the anchoring. Here the anchoring is very strong. When I give some sort of electric field, the anchoring is weakened, and you can see the tilting of the molecules. Perhaps this is giving this color, and at the end, the light is completely shut. So this is the molecular modeling we proposed. And you can see, I studied the capacitance. What is happening to the capacitance? You can see here, when at the shutter, the capacitance is minimum. And when you give the opposite field, whether it is a polarity, different polarity, -5 or +5, and it is a reversible effect, the capacity is increasing. However small it might be, this is a very typical diagram to tell that there is some molecular alignment inside, And physically you can see the shuttering of the light. So this is what we studied through dielectrics. And we have seen some new phases. See, this is a new phase which was discovered in my laboratory. This is called symmetric X, because we don't know what is that phase, we called it X. And you can see this is the worm-like structure. You can see this is like worms. Before in the history of liquid crystals, such a structure is seen. So we call it symmetric X. And we have done some characterization, a dielectric characterization, which is shown here to prove that this is certainly a new phase, not the existing one. We have done the X-rays also. You can see a sharp peak. A sharp peak. This X-ray is at different temperatures. Please see the temperature here. And the sharp peak talks about a symmetric transition. A broad peak talks about pneumatic transition. So here you can see the sharp peak, and the intensity of the peak is also varying. Here it is small, it is large. So all these things are characterized. And now we go to another sample where we studied. This is what we call, I take yet another liquid crystal, which is called, I took dicarboxylic acid, that is glutaric acid, and we have this is the glutaric acid, and then I had used the benzoic acid, and this is the phase diagram of it. So you can see pneumatic, you can see the new phase, which is symmetric X, which is found here in this region, and we have pneumatic C and G, and this is what we call the FTIR, to say that this is formed. We have shown to identify C double bond O and OH peaks, peaks corresponding to functional group C double bond O and OH, and these are the two. That is what we have shown, and this is also published in 2013. You can see yet another azelaic acid, and we made what we call, this is the azelaic acid, and this is a dicarboxylic acid. The dicarboxylic acid is 2 moles. And 1 mole is the acetic acid, and we found what we call the phases, and with oxy and without oxy we did. No, these are 2 different compounds, I'm sorry. So these are the phase diagrams. This is also published in 2011. And many such things like sulfuric acid, filmic acid, all these, this is sulfuric acid, this is filmic acid. You can see just varying this structure, that is the dicarboxylic acid, you are getting new phases and you are getting new what we call properties. This is yet another. So we take the fluoro-alkoxybenzoic acid. Instead of benzoic acid, we took fluorobenzoic acid, and then we got different phases. We got a new phase which is called R, ribbon-like phase, and these are the dielectric. These are called dielectric dispersion curves. So at different temperatures, you can see how it is shrinking. This is published in an elsewhere journal. And this is what we call the phase which is found in our laboratory. This is another phase which is called the ribbon phase. It looks like ribbon. So we named it as ribbon phase. And also, since it is ribbon, we call it R. So this is the phase which we found in our laboratory. And then what is the description? We have seen that how the ribbon is. It is like a large continuous curved ribbons, and each of the ribbon there are disclinations. What is disclination? You can see inner lines. These are called disclination. This talks about the helix present inside the material, and this is the helical structure. It talks about it, and we measured the tilt angle. You can see the tilt angle which. So these are all the things which we did with that sample. And yet another example is shuttering. I showed shuttering with one sample. You can see the shuttering with another sample. So we took the same this fluoro substituted benzoic acid, so fluoroalkoxybenzoic acid, and what we did was this is the conducting area, this is the non-conducting area. We applied the field, and you can see the shuttering. The light is not allowed here, the light is allowed here. So this can be used as an optical shutter, and the extinction can be seen clearly here in these two. So this is, and if you remove the field, the light will be again, it acts as normal. original texture will be retained. So this is what we call the observation and the application. This is also published in the journal, in elsewhere journal. Now we talk about some other things. So here what we did was, when we had that shutter, we measured the helix. So we have different types of helix. That's the reason shuttering is happening. In shutter we have the minimum, the helical structure is almost tending to 0, and we have the maximum in the part when there is no shuttering. So this is how we can see the distinction. And we have also done the voltage, how it is responding. So this is what you can understand the variation of the capacitors in different fields, and you can attribute this curve. Gaussian curve talks about the symmetric variation. You see, whether if you draw a line, whatever you get here, you'll be getting here. So there is a symmetry, whether you apply negative or positive, there is no polarity. Whatever polarity you apply, you will be getting the same curve, and the symmetry can be talked about there. And you can see many shuttering. We found many shutterings in, once we found in one. You see A, B, C, D. As you increase, I can show you here. Once I gave 5 volts, this is what I got. Then I increased to 6.5. So with increment of voltage, you will be getting different what we call textures, and the light shuttering will be happening as you increment the voltage. This can be seen, and this is also published in Optics. And this is another where light modulator. I told what is light modulator. Light modulator is nothing but this is one type of color. I am giving field. Here you can see blue. I am giving electric field 20 volts per micron. Then you can see this becomes another color. You can see how the color is slowly, gradually changing. You can see that. And so this is what we call light modulation. So blue color goes to some other color, orange color, and this is what we call the light modulator. So liquid crystal can be used as light modulators. And we found something like reentrant. What is reentrant? Once you take water, you freeze it, it becomes ice. And there is what we call 4 degrees anomalous expansion of water. That is on the surface, ice will be there. Below it, you will have what we call the water will be there. The fish and all that will be living in that. Even above, there is a layer of ice. That is what we call anomalous expansion of water. Here we are talking about reentrant. A phase will reappear. Once, usually, when you get a phase, for example, you get a pneumatic. Then you cool, you will get some other phase, magnetic phase. You cool, you will get another phase. But in this reentrant, what happens when you get pneumatic? You get some schematic A. You cool, you get schematic B. You cool, again you get schematic A. So reentrant phase is that. So it is reported in literature from 1977 to 2011 had collected. These are all the people who noticed it in different compounds, and we also did it, and we got. You see, we observed it in some phases. So this is probably what we call the textural evidence of it. We have one phase, and that phase, when you apply, it will be getting another phase, and again you will get to see at the same phase. These two are the same phases. Wherein in between, when you give the field temperature, something happens, and again this same phase is coming, which is very, very rare, and this is what we have reported here. We did something about it, and you can see in this to prove that it is reentrant, we made the X-ray diffraction. You can see the peaks at different temperatures, and a sharp peak indicates that it is a schematic phase, and that is what we did. We did the DSE, and we found that what is texturally happening is also happening thermally. You can see the peaks, which are very clear evidence of that. So this is what we have seen. Then we proposed on modeling for it. So we need to know how you can give modeling to something which you have seen. So this is how the mesogens are in one phase, and this is how in between is happening, flipping of the molecules. And when you decrease the field, instead of this way, they are aligning this way. So this is what we call C, and this is re-entrant. You can see just 180-degree phase shift, nothing more. And this is what we propose, which was accepted. You can see this is the helix, and these are other things. So we made a modeling to tell why it is happening, rather what could be the structure, phase structure, when C and C star, when re-entrant phase happens. So there you should take care. You should not contradict the existing principles. You should propose in such a way that all the theories which you propose should also be in accordance with the new phase. So it took a lot of time, and this is how we came out with this proposed molecular alignment. So this is the helix, and this is the molecule, and this is how it is going. This is, you can see the helical structure with the molecule. This is how we propose. Now we come again. My topic is more about applications. So I again want to talk about 6 applications. There are some, I have chosen 6 applications of liquid crystals. You can use them as capacitor. You can use them as data storage devices. That is, optically you can store data, and electrically also you can store. So 2 ways, data storage. Then light filtering. You can use them as filters in and in infrared. So in visible and infrared. And then you can use as light modulators, which I have shown many times. Again, I'll be showing. And then you can use as a thermistor. This is what we published recently in IEEE. So 6 applications I'll be talking here before. So first, capacitor. What is a capacitor? You can talk 2-3 hours on capacitor. What is a capacitor? After all, if you ask a very energetic school student, he says that it is a charge storage device. If you ask an engineering student, he says that it is a filter. It can be used as a filter. Whatever it is, there are categories of capacitor. You have electrolyte capacitor, disc capacitor, ceramic capacitor. Like this, you have many types of variety of capacitor. Broadly, I divide capacitor into 2 ways. One is electrolytic capacitor and other non-electrolytic. Why 2 cases? If you want 1 MFD or more, if you want to store farads, 1 microfarad or more, then inevitably you have to go to electrolytic capacitor. Anything less than that, you can have different types of capacitors. As I told, disc capacitor or ceramic capacitor or whatever it is, air capacitor, all these things. But if you want to store more data, you have to come to electrolytic capacitor, which is which you have an electrolyte in it, and this electrolyte you have to give charge to it. There is a polarity, and if you give the other polarity, capacitor will blast there. So you have to be very careful in giving the polarity, and only then it stores some charge. So this is, I have studied that capacitor, and they are very bulky in nature. I'll be coming to that point later on. So we took one liquid crystal. I don't want to go details into it. This exhibits a room temperature phase, and this capacitor, this liquid crystal can be used as a capacitor. In fact, any liquid crystal can be used as a capacitor, but only condition is that liquid crystal should exhibit liquid crystalline properties at room temperature. Then only you can use it as a capacitor. So we have done it, and we patented this in 2018 on 3rd December. We call it as invariable capacitance for electrical circuits. This is through liquid crystal, obviously. Then what are the differences? Why we need to go to liquid crystal? Because Madhu Mohan is working in liquid crystal. Need we go to it, or is there anything elegant? Certainly there is something elegant. You see, if you take the capacitors, they're all very bulky. If you see the capacitor, the more the value, magnitude, 10 MFD. If you take 100 MFD, will be much bulkier. 10 MFD is much bulkier than 1 MFD. So more the magnitude, more bulky it is. But liquid crystal capacitors are not like that. They are very like paper-like. You take 2 glass slides, and you can sandwich the liquid crystal in between, and you can call it a capacitor. So these are they require very less space. Then working voltage. What is working voltage? If you take a capacitor, what is the working voltage in a capacitor? The dielectric breakdown. So they will be cautioning you, don't go beyond. What is the working voltage? Maybe 20 volts, maybe 10 volts, maybe 30 volts. If you go beyond that, what happens? The dielectric breakdown will happen and the capacitor will blast. So in commercial capacitors, the dielectric breakdown usually happens at very low voltage. But in liquid crystal, it is very, very high. The working voltage is very high. For example, if you want me to tell, it will be hundreds of volts. It is not just 100, maybe 1000 volts per micron. Then the dielectric breakdown will happen. But if you take commercial capacitors, there will be 35 volts, 42 digit. But liquid crystal will be having four orders. So 1000 more than that. Then tolerance. What is tolerance? When you give the capacitor, maybe 1 MFD, how much that value varies with the printed value on that is called tolerance. In resistance, we'll be having lines, gold, silver. These are we draw the lines and we tell the variation. In capacitor also we have that, we call it tolerance. And in liquid crystal, it is very, very small. And then the another problem is leakage current. If you take capacitor, what is leakage current? You charge your mobile, which is having a battery, and you don't use it. After 10 days, you see, you will not have the same charge. What happened to the charge? It leaked out. Because if you take a capacitor, if you charge the capacitor, even if you don't use, there will be leakage current and the charge will be diminishing. But in liquid crystals, it is very, very minimal. But if you take the ordinary substances available, it is very high. And then variation with the frequency. It is very, very high in commercially available capacitor, but in liquid crystals, it is low. And the working temperature is huge. Let me tell, minus 10 degrees centigrade to 55. Whatever may be the temperature, you take some of the capacitor. They will not work at these temperatures because they are not, the working temperatures are not that. To my knowledge, there is no capacitor which can work below 0 degrees. All capacitor, because at 0 degrees it becomes a solid, the electrolyte becomes solid, so it cannot work. But in liquid crystal, it is not the case. In this specific liquid crystal which I talked about, you can have up to minus 10 degrees centigrade. Still it will be. So these are the advantages, and this is the reason we patented it in 2018. And next, memory storage. What is the most important thing is memory. What is memory? We talk about storing and retrieving. These two constitutes memory. And I classified this as electrical memory and optical memory. So you can choose, you can use electrical, that is dielectric current, or you can use electromagnetic wave. So we took this liquid crystal, I'm not going to this liquid crystal details, and we tested these two. I call it 2A, 2B. This is 2A optical storage. Now this is my liquid crystal texture. I gave some voltage, maybe 5 volts I believe. You can see the change in texture. You have bright and dark. You can see the stripes. This texture change to this texture with bright and dark. And for my engineers, they can convert this texture into zeros and ones. Where there is highlight, it is 1. Where there is dark, it is 0. So this way you can store the memory. So this is what we call optical memory. And how do you erase this? You heat it, then it goes to isotropic. Even if you remove the voltage, it retains the same. But if you heat it, then what happens? The texture will be lost and data will be lost. So this is called optical storage. And this is what we recently, 2019, 15th July, we applied for an Indian patent. So this is the optical storage. 2B is electrical storage. What is electrical storage? Hysteresis. You remember that hysteresis curve, which is like a mango shape. Here also, what we did, we took a liquid crystal, we gave the field, we measured the capacitance, and then we withdrew the field slowly. We expected it to retrace the path, but it has not retraced the path. It took another path. So the area which is sandwiched between these two can be used for storage. The more the area, more will be the storage. Here this is patented. So these are two types. One is optical storage, that is to texture. We have proved that optical storage. You can see the lines here. And then electrical storage. This is published in a journal, obviously. And you can see the electrical here. This is what we call it is not retracing the path. So this is what we call the electrical storage. Third, filters. There are, if you are a good student of electronics, there are many types of filters: high pass, low pass, band pass, notch. All these can be realized through liquid crystals. So what we do, we took a liquid crystal, we varied the frequency, we sent the light with the different frequencies, and we measured the intensity. You see here it is a high pass. It is allowing the high frequencies to pass. Low frequencies it is not allowing. Here it is a low pass. Low frequencies it is allowing, high frequencies it is not allowing. This is a notch. You can see a notch. Only this frequencies it is allowing. The notch is from maybe 4750 to something around 5750. And all others are not allowed. So these filters, through liquid crystals, we achieved what we call the optical filtering here. Then we have seen the filtering in infrared region also. What is infrared region? We made a pellet with liquid crystal, and we kept the pellet in the path of IR infrared light, and then we got a band pass filter. You can see the band pass filter here. So this is it is in gigahertz, to be honest. So the bandwidth, that is between this cutoff and this cutoff, lower cutoff and higher frequency, is 204 gigahertz. So what is the low frequency cutoff? This is 504, this is 504, and the high frequency is 708. So the difference between these two is what we call the bandwidth. This is what we call the optical filter in the infrared region, and even this is published in a journal very recently. So this is also patented recently on 14th November 2019. So this is the filter we have seen. So these are the typical examples. If you ask me, you can see liquid crystal as a capacitor, liquid crystal as a data storage device. So we have used optical and electrical techniques to store the data, and filtering. We have seen high pass, low pass, notch, band pass, all these things. And we have also seen the other two. I'll be telling you that. This is what we call the modulator. I said green and light. I told you, I showed you, I don't know whether I showed or not, but here you can see it. You take a liquid crystal, which is showing some color at a particular temperature, and you give a threshold field. Here it is 2.5. What happens? The color of green will change to red. And you remove this field, again it is reversible. Come back. So this is what we call light modulator. You can get with the temperature, you can get but field. So this is the light modulator. This is what we patented in 2017 on 22nd September. So this is a light modulator. Very simple. You take a liquid crystal and you give, it will be showing one, here it is green light. You just give a pulse of 2.5, the color of the entire texture will be changed. So this is light modulator. Then you can see, this is what we published in IEEE, a thermistor. So what is a thermistor? You have two types of thermistor, that is a positive temperature coefficient and negative temperature coefficient. Here we took a glass substrate. This is the liquid crystal cell. And this is not filled with, you can see this is the glass substrate. This is the liquid crystal. These are the spacer. Usually it will be 10 microns. Then you have the active region. This is the active region where that ITO coating is there. And these are the electrodes. You can see the electrodes. This is one electrode. This is another electrode. And this is the polyamide surface for the alignment of the liquid crystal. Then we fill the liquid crystal. And then we have by heating the liquid crystal, we filled it. Then we connected the. This became a thermistor. First time in the history of liquid crystals, we have fabricated a thermistor, and this is published in IEEE very recently, 2020. And this is what all about it. And you can get positive coefficient temperature thermistor and negative coefficient temperature thermistor also. This is one of the applications. So these are what I talked about till now. This is my conclusion. So I talked about the utility of thermotropic hydrogen bonded liquid crystals. I talked about capacitors. I talked about memory storage devices, optical filters, in visible and infrared. I talked about liquid crystal as light modulator. I talked about liquid crystal as thermistors. All these things are true. So this is the essence of my talk, and these are the references. I have huge references which will talk about the different aspects of the liquid crystals. And finally, let me acknowledge, I thank the Sona College of Arts and Science, the management, for giving me this opportunity. In particular, I thank Kadar Nawaz, the principal, and Sridharan, the head of the Department of Physics and Chemistry, and Shankar Narayanan, the organizing secretary of this talk. And also I thank my Banariaman Institute of Technology, the management and the principal, for allowing me to take up this assignment. And also I talk the Science Engineering Research Board, as SERB, for giving me the project to accomplish some of the things which I had shown you. And lastly, my liquid crystal research laboratory teammates who have helped me in many ways in making these things a reality. So these are my acknowledgements. And if you have any questions, you are most welcome to cross me, and I leave the dais to the audience. Thank you. Hello?
Thanks a lot, sir. Thanks a lot. Usually we think of LCD as a means of display. But today, in your talk, we have come to know of so many things that LCD and liquid crystals can do. That was a thorough learning experience, very much engaging through the session. Thanks a lot, sir. And all our participants would have learned a lot, I guess, from your lecture. Thanks a lot. And yes, Varsha.
Thank you, sir, for giving us an opportunity to hear your thoughts on applications of liquid crystals, which is definitely useful for us in gaining knowledge. Now the session is open for queries. Participants can unmute your mic and raise your queries to the chief guest.
Yeah. One more thing, if participants want to ask questions in the chat box, they can post the questions there as well. Otherwise, you can post the questions in the WhatsApp group also.
Sir, good afternoon, sir.
Good afternoon.
Sir, I had a question, sir.
Please, ma'am. Please.
Yes, myself Nilufer, sir. Sir, in hydrogen bonding, how to identify the existence of hydrogen bonding, sir, between particular molecules? Is there
Usually, yes, ma'am. Can I answer now?
Yes, sir. Yes, sir.
Usually, we go for FTIR. If you take a spectrum of the FTIR, you will be knowing the functional groups, C double bond. You know the substance you have taken, and you will be knowing where the hydrogen bond is formed. So that particular functional group will give a peak in FTIR, and that can be easily seen now.
Okay,
So
sir.
usually what we do is we take the FTIR of precursors before making the hydrogen bond. We take that compound and get the FTIR, and after forming the hydrogen bond, we take the FTIR. When we compare both, certainly you will be knowing whether the hydrogen bond is formed or not.
Okay, sir. Okay, thank you, sir.
Okay.
Any questions from the participants? If
Yes, sir. Hello, sir. Sir, good evening,
Yes.
sir. So, good evening, sir.
Good evening, sir. Please.
Sir, liquid crystals, it's like a semi-crystalline. It's exists between the liquid state as well as between the liquid state and then solid state. And so, liquid crystals moves like a liquid. So, in suppose if we take any one particular liquid crystal, what about the friction rate or viscosity, sir?
Actually, we talk about positional order and orientational order, sir. If you take a crystal, you have a lattice where
Yes, sir.
the molecules are fixed, they cannot move. But if you take a liquid crystal, that too in liquid state, that is in state between liquid and solid, you will be talking about positional order and orientational order. Positional order will tell where the atoms are. Orientational order will be telling how the atoms are oriented with respect to a given direction. Basing on the knowledge of this, we can calculate many parameters. Coming to your question, well, viscosity is one well celebrated method to know how we go for refractive index measurement, where we'll be understanding what is the refractive index of that. Through that also we can estimate what is the viscosity of it, or what is the liquid crystalline component in it, sir. Hope I had answered your question.
Yes, sir. Thank you, sir. Thank you, sir. Sir, one more thing. In
Please.
solid, perfect crystalline material, the
Yes.
atoms or groups arranged in a lattice in a perfect manner.
Yes, sir.
Coming into the liquid crystal, sir, what is the order of the atoms or group?
That is what I said, sir. There are called in solids we have three-dimensional lattice. In liquid crystal we have two-dimensional lattice, which are governed by the positional and the orientational order. These two-dimensional lattice are usually they belong to trigonal or more complicated structures, not the cubic, not the very simple structures. There are monoclinic or trigonal structures, and we classify it with the two orders, that is the orientational and the positional orders.
Okay, sir. Thank you. Thank you, Professor. Thank you, sir.
Any other questions from the participants? You can unmute your mic and ask our professor.
Good evening, sir.
Good evening, sir.
Sir, what can we expect in the near future in liquid crystals, sir? I mean, in what kind of a direction is it heading towards?
Yes, thank you, sir. If you take your mobile, you have a liquid crystal. If you take your watch, if it is a digital watch, you have liquid crystal. Go anywhere, display, it is liquid crystal. What more you want? Now, there are we are doping CNT, that is carbon nanotubes, or whether gold particles, single wall or multi-wall carbon nanotubes into these liquid crystals, so that the alignment can be achieved with less voltage. Now, this is what it is being experimented throughout the globe, sir. So that the existing liquid crystals are there. We want to make them work at a lower voltage so that we can save the energy. In that aspect, doping of multi-wall carbon nanotubes or single-wall carbon tubes, there are two types of it again. That is functionalized. What is functionalized? You attach a functional group. Only two functional groups are available, COOH and OH, to one of the graphite, that is rolled CNT, that is single wall or multi wall. That is one type which can be used in the synthesis itself. The other is non-functionalized NWC, multi-wall carbon nanotubes and single wall, which can be simply doped using ultrasonification. This is what the current research is going on in liquid crystals, sir.
Okay, sir. Thank you.